Welcome back, everyone. We're about to take a deep dive, but not into the ocean depths this time. No, we're diving into the heart of a star, or, well, what's left of it.
We're going to talk about white dwarf stars, these fascinating objects that push the limits of physics as we know it.
Right. But we're not stopping there. We're going even further, to the point where those limits get shattered. It all starts with a young astrophysicist, Subrahmanyan Chandrasekhar, back in 1930.
Picture him on a boat, sailing to England to start his studies at Cambridge.
Yeah, a long journey ahead of him, but little did he know he was about to embark on an even bigger journey, a scientific one.
One that would change how we understand the universe forever.
So imagine him there, on that boat, working out equations. He's trying to understand these white dwarf stars, these incredibly dense remnants of stars that have, reached the end of their lives.
At that time, white dwarfs were a pretty new concept. We knew they existed, but we didn't really understand what was going on inside them.
Right, it's mind-boggling, right?
Yeah.
You're the leftover core of a star, something as massive as our sun, crammed into an object the size of Earth.
Talk about extreme physics.
Mm.
And Chandrasekhar, he was trying to figure out just how massive a white dwarf could get. You see, a white dwarf is supported against its own gravity by the pressure of its electrons.
Electrons, those tiny little particles.
Exactly. But under the extreme conditions inside a white dwarf, they're squeezed together so tightly that they start behaving in some really strange ways.
Strange, how?
Well, for one, they can't be squeezed any further. They sort of hit a wall.
Okay, so there's a limit to how tightly you can pack those electrons.
Precisely. And Chandrasekhar realized that this limit on electron pressure meant there was also a limit on how massive a white dwarf could be.
So there's this kind of cosmic balancing act going on inside a white dwarf. Gravity trying to crush it, electron pressure pushing back. But at some point, gravity's got to win, right?
That's exactly what Chandrasekhar discovered. If you keep adding mass to a white dwarf, eventually the gravity will overcome that electron pressure and the whole thing will collapse.
So there's a tipping point, a critical mass, where a white dwarf can no longer support itself.
And that critical mass is what we now call the Chandrasekhar limit.
The Chandrasekhar limit. That sounds pretty important. So what is this limit, this magic number?
Well, Chandrasekhar's initial calculations, done right there on that boat, gave him a value of 0.91 solar masses.
Okay, so 0.91 times the mass of our sun. But wait, I thought the Chandrasekhar limit was supposed to be around 1.4 solar masses. Where's the missing mass?
That's the thing. That 0.91 solar masses was just for the core of the white dwarf. When you factor in the whole star, including its outer layers, the total mass limit comes out to be, you guessed it, close to that iconic 1.4 solar masses.
So Chandrasekhar figured this out on a boat trip. That's amazing. But what are the implications of this limit? What happens when a white dwarf goes over the limit?
That, my friend, is where things get really interesting. That's where we dive into the realm of collapsed stars, extreme densities, and some of the most fascinating objects in the universe. But that's a story for the next part of our deep dive.
All right, we'll have to hold on to the edge of our seats for that one.
Okay, so we've got this Chandrasekhar limit. What happens when a white dwarf goes over?
It's not pretty.
I bet it's not.
Imagine all that mass, that gravity, and nothing to hold it back.
A white dwarf collapses.
Collapses, like shrinks.
More like implodes. It's a catastrophic event.
And what's left after this implosion?
That's where we get into some of the most exotic objects in the universe. Neutron stars and black holes.
Wait, hold on. Neutron stars. Like made entirely of neutrons.
You got it. Remember how we talked about electron pressure supporting a white dwarf? Well, when the Chandrasekhar limit is crossed, even that pressure isn't enough.
So what happens?
The collapse forces protons and electrons to combine, forming neutrons. It's a process called neutronization.
Neutronization? Wow. So you're telling me that under enough pressure, the very building blocks of matter can change?
That's the crazy thing about these extreme environments. We're talking about physics at its most extreme. These neutrons, they get packed together incredibly tightly.
How tightly are we talking?
Imagine cramming the entire mass of the sun into something the size of a city.
You're kidding? A whole star crammed into, like, the size of Manhattan?
That's the density of a neutron star, and because they're so dense, they have incredibly strong gravity.
So strong that they can actually stop the collapse.
Exactly. The pressure from all those neutrons packed together creates a force strong enough to counteract gravity. But that's just one possible outcome.
There's another one.
If the mass is even greater, even the neutrons can't hold back the collapse. And
then you get a black hole.
Black holes. Wow. We're talking about things that are so dense that even light can't escape their gravity. It's mind-boggling, right? And all of this whole chain of events, starts with a simple question about the maximum mass of a white dwarf. That's the legacy of Chandrasekhar's work. It opened up this whole new understanding of stellar evolution.
It's incredible to think that something as seemingly simple as the mass of a star can determine its ultimate fate.
It's not just the fate of individual stars, though. Chandrasekhar's work also helped us understand these incredible explosions called supernovae.
Supernovae.
You know, those incredibly bright events where a star explodes, briefly outshining an entire galaxy.
I've heard of them, yeah. But what do supernovae have to do with white dwarfs and the Chandrasekhar limit?
Well, some supernovae occur when a white dwarf in a binary star system pulls in too much matter from its companion star.
So it's like a cosmic feeding frenzy.
Exactly. If the white dwarf keeps gaining mass and crosses the Chandrasekhar limit, boom.
Boom.
The collapse triggers a runaway thermonuclear explosion, a supernova. The energy released is unimaginable.
So in a way, these tiny white dwarfs can be the seeds of some of the most powerful explosions in the universe.
It's pretty amazing. And there's more.
There's more.
These supernovae, they're not just destructive events, they're also responsible for creating the heavier elements in the universe.
You mean like the elements that make up planets and, us?
Precisely. The intense heat and pressure during a supernova explosion can forge elements heavier than iron. These elements are then scattered throughout space, enriching the interstellar medium.
So we're all made of stardust, literally.
In a very real sense, yes.
Yeah.
And it's all thanks, in part, to the work of Subrahmanyan Chandrasekhar.
That's amazing. So from the fate of individual stars to the creation of the elements, Chandrasekhar's work had a profound impact on our understanding of the universe. But we're not done yet. We've talked about neutron stars, we've talked about black holes, but what else did Chandrasekhar's work reveal about these cosmic wonders? Okay, so we've established that neutron stars are pretty extreme.
Oh, they're just getting started. Remember, we're talking about an entire sun's worth of mass crammed into a space the size of a city.
Yeah, I can't even wrap my head around that kind of density. What would happen if you, I don't know, tried to scoop up a teaspoonful of neutron star material?
Let's just say you wouldn't want to hold it in your hand. That teaspoon would weigh billions of tons.
Billions.
Yeah, it would probably just sink right through the Earth's crust. But it's not just the density that's mind-blowing. The matter itself behaves in totally bizarre ways.
Oh yeah, how so?
Well, under that kind of pressure, the protons and electrons in atoms are forced to combine.
Right, neutronization, we talked about that.
Exactly. So you've got this giant ball of neutrons all packed together incredibly tightly. They become what we call a superfluid.
Superfluid, what's that, some kind of cosmic smoothie?
Ha! Not quite. A superfluid flows without any resistance at all. Imagine a liquid that could climb up the walls of a container or spin forever in a vortex.
No friction. That's crazy.
It is. And neutron stars are already spinning incredibly fast, hundreds of times per second in some cases. So you combine that spin with this superfluid stuff, and you get some pretty wild effects.
Like what? Give me an example.
Well, for one, you get these things called glitches.
Glitches. Like the star makes a mistake.
In a way, yeah. It's like the whole star suddenly hiccups, and its rotation speeds up or slows down just a tiny bit.
And then there's those crazy magnetic fields, right?
Oh yeah, don't forget those. Neutron stars have some of the strongest magnetic fields in the universe.
How strong are we talking?
Trillions of times stronger than Earth's magnetic field.
Whoa, that's got to have some effects.
Definitely. Think of it like a giant cosmic particle accelerator. These magnetic fields create beams of radiation that sweep across space.
Like a lighthouse.
Exactly. And if those beams happen to point towards Earth, we detect them as pulses of radio waves. That's why we call some neutron stars pulsars.
Pulsars, right. Those incredibly precise cosmic clocks. So we've got these super dense, super fast spinning, super magnetic neutron stars. That's pretty hard to top.
Well, the universe always finds a way. Remember, if the mass of the collapsing star is even greater, even the neutrons can't hold back the gravitational onslaught.
Black hole territory.
Exactly. That's when things get truly mind-blowing. Imagine a region of space-time where gravity is so strong that nothing, not even light, can escape.
Yeah, I can't even picture that.
It's beyond our everyday experience, for sure. But we can still observe the effects of black holes.
Oh. How do we do that if they're invisible?
Well, if a black hole is orbiting a companion star, we can see the star getting pulled around by this unseen massive object.
So like a cosmic dance with an invisible partner.
Precisely. And as matter spirals into a black hole, it heats up and emits X-rays that we can detect with our telescopes.
So black holes might be invisible, but they're not exactly subtle.
No, they leave their mark on the universe. And it's amazing to think that these objects, which were once just theoretical predictions, are now being observed and studied in detail.
A lot of that is thanks to Chandrasekhar's work.
Yeah, absolutely. His calculations, done on that boat trip back in 1930, laid the foundation for our understanding of these extreme objects.
It all started with a simple question about the mass of a white dwarf.
And that's what's so incredible about science. It's about asking questions, pushing boundaries, and being open to the unexpected. Who knows what other wonders are out there waiting to be discovered?
Well, that's a great note to end on. Thanks for joining us on this deep dive into the incredible world of Chandrasekhar, white dwarfs, neutron stars, and black holes.
It's been a pleasure.
And remember, keep looking up and keep wondering about the mysteries of the universe. There's always more to explore.